Okay, so let me start. Before I start, uh, so again, welcome back after a semester examination and then a semester break. And uh, in the mid-sem examination, actually, I set the part two, which is MCQ type, and mostly on the FM and noise part. The first part was set by Professor Deepak Gurgaonkar. It was introduction and the uh, amplitude modulation. And in my part, the result was announced the same day, and you must have seen it. And I'm very happy that response was really very good, uh, a reasonably good performance from most of you. So we'll start a new topic, and uh, it is about the transmission line theory. And this is the lecture one for that. 1 minute. One minute. There is some problem. I'm starting after a long time. Just a minute, please. I have to stop it. There is some problem here. For last so many days, I have not used it. Just a minute. Okay. So basically, uh, this part is very important in the sense that when you go for various competitive examination like GATE examination, which is required for PSU's jobs and so on, which are also very, very good jobs nowadays, and also in examination like uh, other examinations like engineering services and so on. And even in civil services, if you wish to take uh, EC as a subject. So this is very important, just like we have understood the basics of communication system. This is also very, very critical in the sense uh, that it is a old theory, but it is also applicable today. Today, whatever we are designing various systems, whether you talk about Bluetooth or wireless systems or any RF systems or any system that you think of today, basically uses this theory. And our language is much different. Basically, I would say it is a RF electronics, high frequency electronics. And when I say high frequency, means it is the frequencies like 800 megahertz, 900 megahertz, 1 gigahertz, 2.4 gigahertz, 5.2 gigahertz, and beyond. And millimeter waves now we see for the 5G. Am I audible? Is it okay? Am I audible?
Yes, sir.
Yes. Okay, fine. So basically, here our electronics is very different. So I would not say it is a transmission line theory. It is a high frequency electronics. It is much different from basic electronics. Basic electronics is normally used for designing the systems like you have done the basic electronics curves as very low frequencies, clovers, and there's few megahertz. So if I start this course with something very interesting, that which you already know in basic electronics, the Ohm's law, and here I say I'm not able to write down. 1 minute. Sorry for that. I think I'm using after 2 weeks, so there seems to be some problem. Uh, so basically, if I say, I don't know why. Just 1 minute. Actually, there's some problem still there in my system. So if I say Ohm's law is not valid here, or what you have learned is KVL and KCL, all these laws are invalid. And that looks sound very strange because we have seen uh, these are very basic laws in designing our communication systems. So that is something very strange. Then how to design it, or what I have learned in basic electronics, does it all went waste and so on? No, it is not so. But we have to understand why these laws are not valid. And to understand this, basically, we have to understand because normally Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, we normally apply when we have R, C, L as the circuit elements. And these are very passive elements. They don't, passive means they don't require any bias to operate. You simply connect a resistor, it doesn't need any bias, and it will give you the required opposition to the flow of current depending upon its value. So here, what happens, your resistor, inductor and capacitor, RCL, capacitor, inductor, they behave differently at sometimes we say RF or high frequencies. How they behave differently, and that is we have to understand. Okay, sometimes we say RF or sometimes we say AC, because normally low frequencies are typically known as DC frequencies. Otherwise, high frequencies are typically known as AC frequencies also sometimes. So these basic components, the resistor, inductor, and capacitor, behave at very differently. It normally don't behave like the way we have seen that they behave at low frequencies. So how do understand this? Let's start with some very basic concepts, and that is something how the difference between RF or high frequency versus the low frequency systems. So what are the challenges there? So to start with that, so I say RF or AC or high frequency versus low or DC frequencies. So basically it is something what you have learned in basic electronics and how this RF electronics is different. And please remember this a course also I do in RF electronics, more detailed one, more application oriented as an elective, and which is I'm offering since last 20 years in this institute, and is a very popular course because that is now the basic of any electronics and communication course for any student nowadays, because typically today we are dealing with the very high frequencies. So the first problem is basically the challenges in the uh, RF or so on. So basically, I'm looking for what are the there is some problem challenges here. So I won't say the problem, but there are challenges are there. One minute, I could not write properly. So just please, there is some problem here. So the first challenge is what we call the presence of stray elements. Let me move to the next slide. So I'm writing here presence of one minute. There is some problem here. Let me restart. Otherwise, okay, now it is fine. Presence of stray elements. Stray means something like we say stray dogs, unwanted, or so it is also the same thing. We call it sometimes parasitic. Parasitic is also a undesirable word or unwanted parasites. So these are the various words for that, but we normally use the parasitic or the stray elements. So these are basically what we call the unwanted. Okay, so that is the first challenge here. Second challenge is why it is giving me problem. One minute. Just a minute. There is some problem here. Just one minute. Some problem is coming. Maybe I have to restart. Uh, you be in the Google Meet link. Okay, so let me try. Yeah, now it seems okay. So I think there is some static charges are getting now in my hand and the whiteboard of iPad. I have to change my gloves for that. Uh, so basically, one is what we call the uh, presence of stray, STRA, or sometimes it is called parasitic or unwanted elements. So that we are going to discuss. Okay, what does this mean? But first, I'm putting the challenges. Second is what we call the skin effect. It is not that skin effect or what we normally face when we lie on the beaches and so on. Our skin gets tanned because of the ultraviolet rays and so on. But here also, our components have a skin effect, which we'll discuss. And third is the radiation problem. That means even your components will start also uh, radiating and so on. And the fourth one, which is also there, is what we call the delay. And delay means the transit time. That means time taken from one uh, to the other port, why it happens. So basically, we start in this fashion to understand what are these problems in detail. So let's start with the part one, which is the delay. Now, basically, what happens? Delay here means the charge carriers, how much time they take from moving from anode to cathode, from one junction to the another junction. So basically, what happens? Suppose this is my a junction, let's say a PN junction device, a diode, which is a very basic element in electronics. Now, at low frequencies, what happens? This distance uh, is much less than lambda at low frequencies, because frequency is nothing, it is C over lambda. And we know that C is nothing, it is 3 into 10 is to power 8 meter per second. So frequencies are inversely proportional to lambda. So here the distance is very small compared to lambda. But at high frequencies, this distance is much larger, or I would say nearly equal to at high frequencies, because junctions are typically very small. Now, when this distance becomes nearly equal to the lambda, which is typically at high frequencies, what will happen? Number of cycles, because this my low frequency signal is like this, just like we have seen a modulating signal, and a carrier frequency, which we use as a high frequency signal, something like this. Now, here what happens when my distance is comparable to lambda, or distance is much larger than lambda, many cycles of wavelength will be completed within that small distance. But here, if I pass a high frequency, low frequency signal through this junction, hardly one cycle will be completed. Hardly one cycle will be completed. So basically, because many cycles are involved, as we see here at high frequency, your delay is much more. Effective time delay is much more as compared to the ones at the low frequencies. This also we are going to discuss later on in much detail, but just to give a very vague idea. And then coming to the radiation part. So I'll move to the radiation part. Now, basically what happens in the radiation part, uh, the connectors, actually, I am very sorry that you are not able to use the labs in the basic electronics also. But in the labs, we use what we called a connectors, which are BNC connectors. Just to give you a very big idea, today is an introductory lecture on this one. And BNC means the British Navy connectors. So during the World War II, first time this slightly high frequencies were used, radar systems were used, And those radar systems were using the cables which are using the basic British Navy connectors, because they were uh, actually invented by a British Navy scientist. So these are connectors. If you see here, when you connect this cable to your oscilloscope, there is always remains some gap. And there is a small gap if it is remaining between the instrument and the cable which is having this connector. So some sort of radiation takes place. That means some of the signal gets leaked through that connector, because that gap is nearly equal to the lambda at high frequencies, as you have seen. Or if it is nearly equal to the lambda, it behaves like an antenna or a radiating element, because antenna sizes are also dependent upon the lambda. Okay. And if they are dependent upon the lambda and they are started behaving like an antenna or a radiating element, so radiation will take place. And radiation is not a good sign, that because if my small signal starts radiating, that means the signal get lost into the free space rather than going into the system or the circuit. So this is another problem. So what is the solution? If you see here in your homes, nowadays we have TNC connectors. If you see the connector that is coming from your cable to your TV or through the broadband to your set-top box, they are called the TNC connectors. TNC connectors is an improvement of basic connectors, and it is called a threaded Navy connectors. So they are threaded, means you can actually screw it like the cap of a water bottle. It has got threading there. Similarly, these connectors were actually then discovered to remove that problem of the radiation. After that, other connectors came into the picture, like N type of connector, SMA connector, SMB connectors, and so on. But that is not of our concern. So after that, we have N, SMA, some miniature connectors, A series, some miniature connectors, B series, some miniature C series. So this is what we call the sub miniature connectors, A, B, C, that is the series. And so these connectors basically are required for the high frequencies, because they are the miniaturized connectors. They are very small connectors. And we need to have small connectors, because suppose I have a circuit of this length, let's say 1 centimeter, and if I pass a low frequency signal through this, okay, so there is hardly any change in amplitude, frequency, or phase. But if I pass a high frequency signal through this system, so this is a high frequency. So many wavelengths take place. So this also is undesirable, and so on. And not only that, these connectors, which are typically we use for high frequencies, SMA, SMB, SMC, they are small in size, as I said. SMA is bigger than SMB, SMB is bigger than SMC. So we are miniaturizing the size, because I want to reduce the size of my circuit so that minimum wavelengths could take place, like it happens in a low frequency. Not only that, we'll find that they are also gold plated. If you, again, I'm very sorry that you have not gone to the lab. Most of the connectors that you have seen in your TV and set-top box and broadband box and so on, you'll find they are all aluminum plated. But nowadays we use, especially for circuit design and other thing, in RF lab, if you find, they are all gold plated connectors. So what is the reason for the gold plated connectors? So this is something like I went to give a vague idea. There happens to be a radiation take place because of the gap, and these gaps were basically taken care of by TNC connectors, okay, or SMA, SMD, SSC, which are the threaded connectors. Now moving further to the two very serious problems. Delay part also I will come back to the same thing again through an example, which I have explained to you just now. Suppose I have a signal, let's say this is my A and this is my B here. Now here, I would say your VB is given as V0 cos omega naught T minus delay. So there will be some delay also. And omega naught is nothing. It is your 2 pi f naught, as you have seen. So this is my point A. This is my point B, and this is my point A. So the signal at B, suppose my signal at A is V naught cos omega naught t. The signal at B is given by V naught cos omega naught t minus delay. That means I can't ignore this delay. If you have seen that earlier in the modulation systems, we simply used to talk about omega naught t or phase part. So delay is related to the phase part also. And so this is very critical, especially at the high frequency design. Let's say one typical example. Let's say I take a low frequency, 60 Hertz. Now in this case, let's say my length is 1 meter. So length of the system is 1 meter and all those things. So in this case, my delay, which is basically in terms of time, will be given by length over speed. Okay. So it is given by 1 meter, and this is given by 3 into 10 is to power 8 meter per second. But basically what we are seeing is omega t delay. Omega t delay. So this is my delay time, t delay. So omega t delay, because we have to deal with the frequency here also. And in the frequency part, as you've seen in the angular modulation, if we say omega naught t plus 5. So there is a delay. So omega naught is a this part. So it is, let's say, 2 pi f naught t delay. And it turns out to be 0.0000012 second. If my frequency is 60 Hertz, f naught. But so I would say in this case, VB is equal to VA, which is equal to V naught cos omega naught t. So VA here I have not written, it is V naught cos omega naught t. So here in this case, your VB is nearly equal to VA. That means we don't expect any delay, as you've seen at the low frequencies. But same thing, if I increase the frequency, and omega t will also increase, and that means there is a considerable delay. So let's take that example now. Here I've taken f naught is equal to 60 Hertz. Now if I take f naught is 1 gigahertz. Okay. Which means 10 to power 9 Hertz. Okay. In this case, my omega t delay or omega naught t delay turns out to be 20.94 radians. So it will be in radians because omega naught t. And if I go this one also, it is not second, it is in radians. Okay. So here it turns out to be 20.94 radians, which means 6.67 cycles, complete wavelength cycles. So many are completed because your 180 degree is equal to 2 pi radian is equal to 1 cycle. And we have known this is my 1 cycle. So this corresponds to 1 cycle. So that means 6-7 cycles will take place. So in my circuit, if you see here, almost now 6-7 cycles will take place. And not, because of this, there are multiple reflections also there. Okay, signal going from one port to another, coming back to the same port and so on. And in this case, if I calculate my VB, it turns out to be 0.49 volt of VA. So roughly 50%. So suppose I give a 5 volt signal, it turns out to be 2.5 volt signal because of this transit time effect or the delay. And that is a serious problem. So if I have a circuit size of say 1 meter, which I have taken for simplicity, 3 into 10 to the power 8 meter per second. So at low frequencies, my one wavelength will be there complete. Hardly any change. So whatever the voltage I gave it there, it turns out to be my same voltage at the other end. But at a high frequency, same length, I found it is 20 radians. That means almost 6 cycles or 6 to 7 cycles will be there in the same this one. And because the signal is not going simply forward, it is bouncing back and forth, which gives rise to the multiple reflections also. And also, it will also reduce my voltage considerably. So typically what we normally have seen in the basic electronics, if I give a 5-volt signal, I go to the other point, also I get 5-volt signal. But here I won't get. That is the problem of the delay. So two problems we've discussed, the delay and the radiation. Coming to the two major problems. Now, these are the two major problems. One is what we call the stray elements, and another is called the skin effect. So first I will just talk about stray elements. And then we'll move to the skin effect. And stray elements we have to come back because that is something like a very, very big problem. So basically, moving to the point one again, and we'll come back to that one. At low frequencies, what happens? Your R, L, C, they are all fixed values. When I say fixed values, it means fixed, we say lumped. Lumped, as you see, we say the lump in a throat. That means something is there, solid thing is there. So they are the fixed values. And we typically, we know that we express them in ohms, kilo ohms, millihenries, microhenries, capacitors we have in microfarad, nanofarad. So all these things we know that they are expressed in terms of the fixed values like henries, farad, and ohms, and so on. But at high frequencies, what will happen, which we'll discuss also later on, but these elements are not fixed. They are distributed. They become distributed. Distributed in the sense that their values go on changing at every point on the line. Okay, suppose I see a resistor here. At one point, it is 5 kilo ohm. At other point, it may be something different. At other point, it may be different. It will start behaving differently. Why? So that's I will say. We'll discuss in slightly later, maybe today only. So they become the distributed values. So typically here, as I said, our language is very different here as compared to the basic electronics, because here my components become distributed. Why they become distributed, I will explain to you. Their units are ohm per unit length, or let's say millihenry per unit length, or microhenry per unit length, or let's say microfarad per unit length. Length could be in centimeter, or could be in millimeter, or could be in nanometer, or whatever you call, but they are expressed in terms of per unit length. They are never expressed because they are not fixed. Their value go on changing. So at every length, their value will be different. So we define in terms of per unit length. Again, we'll come back to this point slightly later. But we'll understand the another serious problem, which is the challenge, is what we call the skin effect. So I'll come to that point. It is called the skin effect. So let me first explain to you what is skin effect. Suppose I take a wire, a simple wire. I think RLC are the basic components, but before that RLC, the very basic component that comes into our mind is a wire. Now, if I have a cross section of a wire, something like this, okay, so this is a cross section of a wire. So if I pass a DC current through that, or a low frequency current through that, which you normally have done at the basic electronics level, the entire cross section of the conductor is used for passing the conductor current. Entire cross section of the conductor is used, something which you may not have noticed, and it is difficult to notice because you pass a current to a wire, you don't know what is happening to the charge carriers inside that wire. So basically what is happening at low frequencies, if I write down here, or DC frequency, which we normally say because they are normally low frequencies, or low DC current, entire cross section of the conductor is used to pass the current. Entire cross section of the conductor, which in this case is wire, is used to pass the low frequency or DC current. Okay. So that happens at the low frequencies. That means if my wire is 6 centimeter thick, the entire 6 centimeter cross section will be used for charge carriers and the current flows there directly. Okay. But what happens to the high frequencies? So as we move to high frequencies, what will happen? As we move towards high frequencies, okay. Now this is my same cross section of the conductor. Okay. So here I pass a AC current or a high frequency current, high frequency or AC current. In the previous case, if you see, we have passed about the DC or low frequency current. So here what will happen? The current, the charge carriers tends to flow only on the skin, and entire cross section is not getting used. So if you see here, the charge carriers tends to flow only on the skin of the conductor. Okay. So what happens here? So I will write down here at high frequencies what will happen? At high frequencies or AC, only a portion from the skin of conductor, top skin, okay, skin is always on the top, is used to the pass the current. So not the entire cross section is used. Entire cross section is not used here. Not used here. And they actually this depth up to which the current flows inside the conductor is represented by delta, which is a small delta, Greek delta. So this is the depth, which is what we call the skin depth. So I define this delta or skin depth. It is called skin depth, very important concept for us. So this is nothing. It is a Greek delta, small. There is a Greek capital letters also, and delta is the capital letter for the Greek delta. But we'll use a small, normally it is used throughout the books and various books, a small delta for defining the skin depth, not this one. Okay, we'll not use this one. So this is nothing. It is basically called the depth of penetration. How much the current penetrates inside the conductor. So because entire cross section is not there. And this is the depth of penetration where my signal amplitude, whatever we give, so I remove this, is 1 by E or 36.8%, or sometimes people write nearly 37% of its surface, which is the maximum amplitude. So how to define this skin depth? So basically what happens, as you move towards high frequencies, because of Faraday's law, maximum position to the flow of current is near the center of the conductor. Okay. And because of this, current tends to flow only on the skin. So this is what we call the skin effect. And how much below the skin the current flows, as we see here, is defined what we call the skin depth, or it is a Greek letter delta, small delta, and it is typically defined as, we have to define certain value where the signal amplitude is 1 by E or 37% of its maximum value. Suppose I gave a signal at 5 volt at the signal, say 5 ampere at the signal. So where my signal current signal strength drops to 37% of 5 amperes, that means around 2 amperes or so, 40%, nearly something. So that is how we define the skin depth, because current will not immediately diminish at a certain point. It will slowly decrease, and it will be reduced to zero at the center at high frequencies. Okay, so if I explain in a simple way like this, uh, so this is my cross section of a conductor, I am saying, and up to this point, let's say my current is flowing. Okay, I could not write. So this is, let's say, the radius R, and this is my skin depth, which we have seen here. So what happens here, if I plot with respect to this distance, R is equal to 0, and here it is R. At certain point, R is equal to delta, which I'm defining the skin depth. And if I plot this thing, the current density, let's say it is my J naught. Maximum current density. So this is nothing, I could say, defined as the maximum or surface current density. So current density means current per unit length. Okay, so current density is defined as current per unit length or current per unit area. So it is defined as 0.37 J naught. And this is like an exponential curve, as you say, it decreases exponentially. So it is in exponential in nature. And typically this skin depth is given as an empirical formula again, as I said. We normally speak in terms of, sometimes in terms of empirical. Empirical means not derivable. As I told you earlier also, in my Coulomb's law or basic Coulomb's law or basic Biot-Savart law in electricity and magnetism are, or gravitational law, they are all empirical laws. Okay, they are not proven by any mathematical derivations. So this is given as 2 omega mu sigma, or it is also given as 1 by pi f mu sigma, because my omega is 2 pi f. So this is the skin depth. That means up to what? So basically, if you see here, delta is inversely proportional to square root of frequency. Okay. So as we increase the frequency, your delta tends to decrease. Your delta tends to decrease, as we see here in this figure also. So everywhere it is these charge. Okay. And delta tends to decrease. That means at lower frequencies, my delta is nearly zero, because frequency is zero, so delta is infinite. That means it is taking the entire cross section of the conductor to pass the current. But as we go on increasing, my current tends to flow on the skin. So this is what we call the skin depth, where we know that mu is your permeability of the medium, because every wire has got a conductivity and permeability, and sigma is nothing, it is your conductivity. If you are using a copper wire, the conductivity will be different. If you are using a gold wire, the conductivity will be different, and so on. So let's take one example based on that. So so what I'm saying, the current tends to flow only on the skin up to skin depth, okay, which is dependent on frequency. on frequency. So this is called a skin effect. Okay, let's take one example. Suppose I take a simple copper wire, which we normally use. Okay. Now, let's take the frequency as 1 megahertz. It is not a very high frequency. Sorry, first I will start with the low frequency. Let's say I take 60 hertz, nearly DC frequency. Now for copper, your mu is equal to 4 pi into 10 to the power minus 7 Henry per meter. So this is nothing Henry. I think you all know that. And this is nothing meter. And sigma, which is the conductivity, it is right as 5.8 into 10 to the power 7 Siemens per meter. So this is what we call the Siemens or ohm inverse or mho, MHO. Inverse of ohm is MHO. So it is basically 1 by R. So conductivity is nothing, it is 1 over resistivity or rho. Okay. So this is what we call the Siemens or so on. So if I take frequency as 60 hertz, your delta turns out to be 1 by under root of pi f mu sigma. It turns out to be 0.85 centimeter. So it will flow up to 0.85 centimeter. Suppose I have a cross section of wire of 1 centimeter. So it is taking almost the entire cross section. And let's take now f equal to 10 to the power 6 hertz. That means 1 megahertz. Forget about 1 gigahertz. Let's increase to 1 megahertz. In this case, my delta turns out to be 0.007 centimeter. So same wire. Now my current just flows only on the periphery. And today we are talking about the frequencies of interest to us 1 gigahertz or so. That means 10 to the power 9 hertz. Can you imagine what will be the delta? Delta will be 7 into 10 to the power minus 6 centimeters, something around that. That means 7 microcentimeter. So hardly any current. So I am giving the current, but it is not flowing. And that is a big challenge. So skin depth is a big challenge. What is the solution for that? Now, solution is that nowadays, if you see, as I told you in RF lab, when you will be doing the experiments in the later as elective, it is the costliest lab in this institute because even my connectors are gold plated. Why they are gold plated? Because my skin depth is better in that case. So everything is gold plated. Just to give a fairly good example, RF is a very important subject nowadays. Earlier, it is used by even in the computers, in the automobile industry. Also now we have all GPS and other systems which need RF and all those things, collision avoidance system and so on. Take your example of a computers. Earlier used to have 100 megahertz computer or something like that. But nowadays, you are having a 3 gigahertz processor. And if you open up that 100 megahertz, you will find that PCBs, almost all the lines used to be copper or aluminum. But nowadays, if you open up your laptop or mobile or something like that, that processor, the motherboard, is all gold plated. The reason is that we have to increase the skin depth. So I have to use a better material. So just like if you recall that when we used to get a credit card, they ask your income. If you have just have a very low income, they will give you a silver credit card, then they will give you gold, titanium, platinum, and all those things. Like in the credit card industry that is happening. Same thing is happening in our system design also. So basically, there is a big requirement of RF engineers also in these computer industry, IBM and HP and Dell and all those things. Because who is going to design? Basic electronics engineer can't design. So RF electronics is the norm. But as I said, to understand the RF electronics, you have to first understand what is the basic electronics. Because it is like that. Suppose I give you an energy drink just now, when you're relaxing, you won't appreciate it. But when you run for 1 kilometer and if I give you energy drink, then you will appreciate that. Because you have learned what are the problems encountered there which is not possible now. So similarly, what are the challenges we had there that I'm passing the current, but I'm not getting the current? It basically because of the skin effect and so on. So this was about the skin effect, the third challenge. And the fourth challenge, again, I'm coming back to the presence of the stray elements, because this is something like very much time consuming. In the sense, we have to discuss for each and every element. So I will start with, again, number one, coming back to the number one. This is the presence of stray or parasitic. Unwanted is obvious, but we use these words quite often, presence of stray elements. Now let's understand what it means. Where these elements are present. So they could be present between conductors of circuit, because in a circuit, I may not be having a single conductor or single wire. I may be having 2-3 wires. So there may be stray elements between the two conductors of the circuit. They could be present there. Also, they could be present between the various components of the circuits. Suppose I have 2 resistors. The presence element could be there. And in our circuit, normally we have a VCC and ground. So there could be stray elements between components and ground also. So there are various possibilities of presence of the stray elements. Let's start with first example, wire, because we'll know that wire, R, C, and L, these are the very basic components. And before the even R, L, C, and L, wire is a very basic component that we used at this thing. So let's start with wire. Now, if I have to understand the wire, I have to find, anything could be understood very easily if I understand the equivalent circuit of the wire. So I need to find what is the equivalent circuit of the wire at high frequencies. Then only I can understand this thing very well. So equivalent circuit of the wire at high or AC or RF frequencies, whatever you call. So it will be like this, because wire is made up of certain material. Okay. There may be carbon there may be something like this, and then it will be a copper cladding and so on. Because it is having certain material, there will be some resistor of that, some R because of that. And because it has a certain inductance of its own. Okay, wire is having a certain inductance of its own, XL, self-react inductance. So it will have certain inductance of its own. And this is what we call the XL, or it is given as J omega L, or it is also given as J 2 pi FL. So this is what we call the inductive reactance. Okay, it is expressed in terms of ohms. Inductance is expressed in terms of this thing. And this R is basically because of material of wire. And this inductance is the self-inductance. And this self-inductance is given by XL, which is nothing. It is J omega L, and which is nothing. It is J 2 pi FL. So what happens here at low frequencies, your F is nearly equal to 0. So XL is equal to nearly 0. So there we don't consider the equivalent circuit of the wire at low frequencies, because it is simply we connect it and there is no inductive reactance and resistance is very, very small. Basically, it is the inductive is contributing because frequency, if I increase the frequency, as we see here, my inductive reactance becomes very high. And that will change my entire circuit composition. Okay. That instead of a simple zero reactance, now I have to consider a well-defined inductive reactance given by J omega L, and which also increases with the frequency. Okay. So this becomes my equivalent circuit of a simple wire. Okay. At low frequency, we treat it like this. So this is my DC or low frequency equivalent circuit. So this is my DC equivalent circuit, simple wire. But now I can't treat it like this. I will consider there is a resistor also there, which is because the material, though even it is low, we can't neglect it. But there is a considerable inductive reactance, because inductive reactance is basically dependent upon the frequency. And as we see here, as we increase the frequency, J2 by FL is going to increase, and so my inductive reactance. So that is a challenge. So this becomes my like a wire. So wire will not be simply uh, a DC equivalent circuit where I simply take it like this. I have to treat it like this. Okay. So this is a simple wire. Just to understand how this wire is very important, because all this wire inductance is very important, and it depends upon the diameter of the wire. Obviously, length of the wire is also important, but length I will choose basically what is desired. Suppose I need a 5 centimeter wire to connect the two circuits which are 5 centimeter apart. I have to use that length, but diameter I can surely choose as per my requirement. And to understand this, we follow what we call the American wire gauge system. I think you must have done two experiments in class 10th physics. Very first two experiment, vernier caliper to measure the diameter of a coin, and the screw gauge to measure the gauge of the or the diameter of the wire. So there we follow the American wire gauge system, which was initially started by Americans, but now it is a standard system. So sometimes we say nowadays we use the word standard wire gauge system. So basically, SWG or AWG, they are coming in various sizes. You can't choose any diameter. If you go to the market, there are only certain diameters are available of various gauges. If you see the screw gauge also, there are various gauges are there where the diameter holes are there. You put the wire and you will find to know what is the gauge of that wire. So various gauges are available. Let's say AWG 50, AWG 44, AWG 36, 32, 26, 20, 14, like this. It means that diameter D is equal to, 1 mil. It means D is equal to 2 mils. I will explain to you what is mils. It means D is equal to, 4 mils. So they are the standard. It means D is equal to 8 mils. It means D is equal to 16 mils, and so on. And what is this mils? What is this mil? 1 mil is equal to 1000 of an inch, or 25.4 centimeter by 1000, because 1 inch is 2.54 centimeter. 1 inch is 2.54 centimeter by this one, or it turns out to be 0.254 centimeter, or 0.0254 millimeter. Okay, am I right? 1 inch is 2.54 centimeter or 25.4 millimeter. Okay, so it turns out to be that one. Okay, so I simply put it like this. Just kind of. Why we treat in mils? Because for us, meter is a very big value, because dimensions are very small, wavelengths are very small at high frequencies. Even centimeters and millimeters are very big values for us. So normally we speak in terms of mils here, okay? Because the wavelengths are very small. So even millimeter is a very large value. So our language is again different here. We never speak in terms of the millimeter, centimeter, and so on, rather than we speak in terms of mils. This standard wire gauge system also uses the diameters of various gauges. Okay, that is 1 mil, 2 mil, 3, 4 mils, 8 mil, 16 mil, 30. If you want to choose any other diameter, you won't get in the market at all. So this is the wire gauge system, which we typically, when we use the mils concept and so on. The next, so we have seen that because of this resistor wire, that was a slightly different thing, American wire gauge system being. But important thing is here is what you have just now said, a wire which was simply like this, for us, it has become like this. That means a resistor and an inductive reactance become a very critical part. So before using the wire, I have to first find out what is the value of R, what is the value of XL, and XL and everything, the inductor of the wire, inductance of the wire depends upon the diameter, and that's why this diameter is very important. So here, this thing very so this is my RF circuit or equivalent AC high frequency circuit of a wire, equivalent circuit of a wire. So I can't simply use this. I have to first calculate that, which we never bother to use any thing in our basic electronics. In basic electronics, whatever wire is lying on the table, you must have done even in your homes also, any wire you use, and it gives you perfect result and also on. But when I'm designing a system, when I'm designing a circuit, like say for mobile phone, for my PCB, for my TV PCB, and so on, I have to be very, very careful in choosing the wire length and diameter and so on. So these two elements are called the parasitics. These two elements are called the parasitics for wire. That means they are undesirable. But they have no significance at low frequencies. Low significance at low frequencies, because at low frequencies your inductive reactance is nearly equal to zero, and R is anyway a small value, typical small value. R is basically comes up because how much resistance is to be provided. So sometimes you have to use the carbon filling in my resistor. If I need a high wattage resistor which can withstand large power and so on, otherwise a simple metal will resist the flow of small current also. Okay, so that is something about the presence of stray elements even in a wire, which we can't ignore. Then comes the three very basic components. Okay, wire is not a component, but it is something like a very standard element that we use. And the three basic elements that we encounter in our uh, uh, lives or circuits is R, C, and L. So resistor, capacitor, and inductor. So basically in our next lecture, we'll first find out what is the DC equivalent circuit or the low frequency circuit. And how it changes to the AC equivalent circuit or high frequency equivalent circuit. For DC equivalent circuit, we know my resistor is denoted by this, capacitor is denoted like this, and inductor is denoted like this. Or if the capacitor has a polarity, it could be denoted like this, plus and minus. Okay, but how these things are represented? So these are the DC equivalent circuits of R, C, and L, which you are aware of. But AC, they'll be totally different there. So that we'll understand in our next lecture. And another important thing, which I will just give you as a curiosity, if you happen to use the earlier TVs, which used to be the big ones with big capacitors, with big inductors in my circuit there, and similarly my desktop computers and so on, the PCBs used to have very big inductors and capacitors. Now, if you see, everything has become slimmer. Your TVs have become earlier CRT tubes were there and all those things, big PCBs, big capacitors. Now they have become slimmer. Your mobile phone has become slimmer. Your uh, laptops have become similar. Sorry, slimmer, slim. Why they have become slimmer? If you see, you will not find any inductor and capacitor there. But can we have any circuit without inductor and capacitor? It is impossible. I need all these circuits, all these components. Suppose I'm designing a tuning circuit, I need a LNC filter, I need a LNC, RNC. Okay, so I need these things, but where they have gone? And here also in my PCB of my laptop also, uh, uh, your 3 gigahertz processor. So you need inductor, capacitor, resistor there. You won't find them. So where them are? Because now your PCBs have to handle high frequencies, and they have taken a new avatar. They have come in a different avatar. What is that avatar? That means the different avatar is that they have come in the form of a printed lines only. Printed line. Okay. And that is the new avatar. Your line is representing an inductor, another line may be representing a capacitor. So how that is possible? How I can represent a inductor with a line, a capacitor with a different line, and inductors also can have a very values very from 0 to infinite henries. Capacitor can also have. So how to deal with that particular value? That is something you will get answer in this one. So they have come in a different avatar. So as I said, the transmission line theory is very old theory, but it is still applicable today. It's still applicable today because we are designing our systems in that frequency. And that's why it has become a very, very important topic for various examinations and so on. And considerable weightage. It is such an important weightage is given to them that if you take this course very seriously, of the 12, 13 lectures, at least you will be able to comfortably do 15 to 20% of these exams very nicely. And here, as I have done earlier, we'll do everything here, mathematical, everything here. And I will share these slides with you and my video recording also, as I previously we have done. Okay, but those who have joined late, still we are continuing with the classes in the online mode. And uh, uh, as I said, the part two of the examination was set by me, which was mainly on the FM and the noise. Part one, which was part two was MCQ type, which was set by me. Part one, which was more theoretical type, which was said by Professor Deepak Gongaonkar. He always appreciate that type of thing. So yes, but he focused on the introduction and the amplitude modulation. For my part, you must have seen the result. I am very happy. Fairly reasonable performance from most of you, and that's the same thing I expect in my this series of lectures, which is also very interesting, equally interesting, as you must have noticed in the first introductory lecture. So we'll start in the next one, continued with the presence of the stray elements, but more with the R, C, and L. And then we'll move to the transmission line theory, because transmission line theory is the basis for that. Okay. So we'll stop it here. I will share this file in my Google Drive with all of you. Any questions? Nothing in the chat box. So I stop it here and we'll continue in our next lecture.